Hi, this is Plant Design SKKK4824 Plant Design Project. We are from Group 5 Aluminium and we are producing 7,025 kilomole per 3 day of ethanol. This is the list of our members, and the first thing that we'll be discussing will be the improvement made after the interim presentation that will be explained by Dinesh.
Next, I will present about the process improvements for the Aspen Plus simulations which we have done after a few corrections. The diagram illustrated in this slide is new stream results after changing some inputs in the Aspen Plus and the simulation was run again. I would like to specifically mention the mass flow and enthalpy flow unit in the simulation is kilogram per hour and kilojoule per hour, which will be later converted to kilogram per 3 day and kilojoule per 3 day respectively for percentage error calculation. For the mass balance comparison between manual and Aspen calculation, the error was bigger in stream 19, which is 44.48%. This is probably due to some inaccurate specification input for parameters such as temperature, pressure for some units, or it can be some inaccurate thermodynamic assumptions. Unlike mass balance, errors are much more significant during the energy balance computations due to discrepancies in steady states between manual and simulated values, and some components are not viable in the Aspen Plus, such as yeast and nitrogenous compound in the related streams, which cannot be run in Aspen, and other incorrect thermodynamic assumptions.
We move to the process heat integration. So what is process heat integration? Process heat integration is the systematic and general method for designing the integrated production system with the aim of using the energy efficiently and reducing the environmental effects. Heat exchanger network, or HEN, is the network designed to minimize the energy consumption through the maximization of heat energy recovery, which will then reduce the operating cost. It allows the heat to transfer from hotter streams to cooler streams by using some heat exchanger. This process is more profitable for long-term process as it helps to save the operating cost. What are the steps that we need in process heat integration? The first one is we need to find the pinch temperature. To find the pinch temperature, we need to identify the cold streams and the hot streams. This table shows which is the cold streams and the hot streams. To identify it, cold streams is the stream that from low temperature to the high temperature, while hot streams is the hot temperature to low temperature. After we get this data, we have decided to use 10 degrees Celsius as the temperature minimum. Then this table shows the new data after we minus it with the 10 degrees Celsius. For the cold streams, we didn't need to minus 10 degrees Celsius, but for the hot stream we need to minus it with 10 degrees Celsius. Then the new data after we minus it with 10 degrees Celsius will times with FCP to get the new stream enthalpy. Now we go to the problem table algorithm. After we got the new data from the previous table, we will draw the cold stream and the hot streams in this figure. So we will get the new delta T and the new FCP from the differentiation of cold streams and the hot streams. Then we will get the new enthalpy for this table. In heat cascade diagram, we will find the pinch point. First, we will start QH with 0 and add it with the enthalpy streams. If the 0 did not appear in any temperature point, we will choose the number that are far from 0. For example, is negative 3810 and 973 kilowatts. Hence, we will get 30 degrees Celsius as a new pinch point for the cold temperature and 40 degrees Celsius for the hot pinch temperature. We will also get a new QH and a new QC as it stated in this figure. So we will find a new percentage saving. So the heating requirement from hot utility before integration is 9,934 kilowatt and the cooling requirement is 6,826 kilowatt. With a formula which is heat before heat integration minus heat after heat integration over with heat before heat integration times 100. The percentage saving for QH is 61.64% and for the QC is 89.7%. After that, we will draw the grid diagram to locate heat exchanger. From this diagram, we will get 3 heat exchanger and the total 3 heaters will equivalent with minimum heating requirement and also as a 2 cooler will same with minimum cooling requirement. Heat exchanger, then we will draw a new PFD with heat exchanger located at the specific streams.
Next, I will talk about the wastewater treatment. The type of waste generated in our plant is sulfuric acid, nitrogen, yeast, glycerol, and toluene. Therefore, we have come up with a few treatment methods to remove these wastes. 3 different stages of treatment method were proposed, which is primary treatment, secondary treatment, and tertiary treatment. Primary treatment involves sedimentation of solid waste within the water. Wastewater is passed through several tanks and filters that separate water from contaminants such as sulfuric acid and nitrogen. Settling pond is also applied to allow more suspended solid such as the yeast to be separated from the wastewater. The secondary treatment includes trickling filter, rotating biological contractor (RBC) and membrane bioreactor (MBR) in a common ways. In our plant, glycerol and remaining suspended solids from primary treatment is further removed through membrane bioreactors, which are actually activated sludge systems using a membrane. The membrane component uses low pressure microfiltration or ultrafiltration membranes and does not require secondary clarifier. The technology permits bioreactor operations with considerably higher mixed liquor suspended solids concentration than the conventional activated sludge system, which are limited by sludge settling. The tertiary treatment usually removes specific pollutants including phosphates, nitrates, and other partially soluble hydrocarbons. For our plant, it removes toluene. Tertiary treatment includes reverse osmosis, ion exchange, chlorination, ozonation, or adsorption onto activated carbon. So when we come to our plant, after separating yeast from wastewater, the yeast will be pre-treated by chemical oxidation using ozone to destroy the organic contaminants in the yeast before discharging into the river.
Hi, the next I will be explaining about on our equipment sizing and costing. So in this chapter, these are the equipments that are included for the calculation of sizing and costing. The CE index used throughout the plant is 607.5 from the year 2019. All the cost indices calculation equations are all based from the book of Product and Process Design Principles, Synthesis, Analysis, and Evaluation, the 4th edition. Next, we have the distillation columns where we have The material used are stainless steel, as ethanol and our product has corrosive properties. From there, we calculate also the weight and the number of tray, and ultimately giving us the purchasing costs for all the 3 distillation columns. Next is our heat exchanger. In total, we have 3 heat exchangers, 2 coolers, and 3 heaters. The material used for the construction of the heat exchanger is after careful consideration of the probability of corrosion occurring. We calculated the area needed and also the costing for it. So from here we can see that the fire heater we constructed it using carbon steel, and these are the costing for it as well. Next, we have the equipment sizing and costing for the vessels. The first mixer we have here is for the dilution of molasses. The second one is for the acidification of our water mixture by adding in sulfuric acid. And then we have our scrubber to recapture ethanol and to separate CO2. So after the calculation of the sizing of the corrosion allowance, the shell thickness, the weight, and all, we are able to calculate the costing for these vessels as well. Then we have our sterilizer vessel and fermentation tank. Sterilizer vessel is to sterilize unwanted bacteria in the water mixture. So the material is stainless steel, and this is the costing. For fermentation tank, the material is low alloy steel, and this is the costing. The reason we choose low alloy steel is to have a tad bit of corrosion resistance, and also to reduce the costing factor. Then we have our storage tanks. For our storage tank, the sizing can be found here, and this is the purchase cost for storage tanks. Then we have our ultrafiltration membrane. The purpose of this ultrafiltration membrane is to remove ash and dye from molasses. So we have the mass flow rate, we have the density, the total mass per batch, and then the material of construction is a flat sheet membrane. So this is the sizing and then the costing for ultrafiltration membrane. And lastly, we have our pumps. We have a total of 3 pumps. The type that we're using is VSC with RPM of 1008. With respective flow rates, we can calculate the purchase cost and the CBM of the pumps.
The process control. What does it indicate to? Yes, it indicates the condition of a plant process where any upset can be controlled and following emergency action to be implemented. Without suitable and reliable process controls, an unpredicted process occurrence cannot be monitored, controlled, and eliminated. So, we're going to talk about the individual equipment P&ID diagram. First one is the distillation column. This column is used to separate the main product ethanol from water, sucrose, and glucose, thus to increase the purity of ethanol up to 99.9%. So, the process control system has been designed with the aim to control the pressure of the distillation column at 1 bar, to maintain the feed ratio to the column, to maintain the level of column so that flooding can be avoided, and lastly to control the composition of column effluent at desired level. So what does PT means? So it means pressure transmitter. PIC, it means pressure indicating controller. PIH means pressure alarm high. PIL indicates pressure alarm low. LT level transmitter. LIC level indicating controller. AT composition transmitter, and AIC composition indicating controller. This process control also been applied the same for the isotropic column and recovery column. So this is isotropic column. It is used to separate ethanol from water. So as you can see, the control objective for isotropic column is the same with the distillation column as I mentioned previously before. So this is the recovery column. In this column, water and ethanol are fed so that it can be recycled back into isotropic column. The process control system has been designed with the aims to control the pressure of the column at 1 bar, to maintain the level of refluxium and column so that flooding can be avoided, and lastly to control the composition of distillate and bottom product. Move on to the heat exchanger control system. It is used to control the temperature of stream at desired value so that the process can operate optimally and safely. So what does the TT means? It indicates temperature transmitter, while TI indicates temperature indicator, and TH indicates temperature alarm high, and TAL is temperature alarm low. This is the pump control system. It is used to control the outlet stream pressure at desirable value for the pump to operate optimally and safely. What does PT indicates? It means pressure transmitter, while PIC indicates pressure indicating controller, PH pressure alarm high, and PIL pressure alarm low. Next is the mixer control system. This mixer is designed to mix the molasses with water before entering the fermentation tank for reaction. The control objective for mixer is to maintain the total sucrose, glucose, and water flow rate at a desirable level. Ultrafiltration control system. It is used to remove the suspended solids such as ashes from the system before being sent to the fermentation tank for reaction. These ashes need to be removed in ensuring no impurities in the products and blockage in the stream, so that the process can operate optimally and safely. Therefore, the flow rate of molasses feed need to be controlled before entering the ultrafiltration. As for the fermentation tank control system, the process control system has been designed with the aim to control the flow rate of the tank, to achieve desired composition of ethanol produced, and to maintain the temperature of the fermentation tank itself. Lastly is the scrubber control system. This scrubber is designed to absorb carbon dioxide from mixture of carbon dioxide and ethanol. The process control system has been designed with the aim to control the outlet flow rate of the scrubber, to achieve desired composition of ethanol produced, and to maintain the temperature of the scrubber itself. So, as you can see, this is the overall equipment PNID diagram of production of ethanol from molasses. Move on to the process safety study, we will talk about the general safety assessment and potential hazards specific to the plant, and also the hazard study on major equipment. Consideration of various chemicals. Safety consideration and precaution have been gathered concerning chemicals involved in the process that may pose a hazard to the operators. For example, carbon dioxide, it will cause headache, dizziness, vomiting, and confusion. Therefore, be aware of any sign of all the symptoms above if we are exposed, and keep all self-contained breathing apparatus readily available for emergency use. For sulfuric acid, it is corrosive and reacts violently with water. Therefore, it is important to use gloves, mask, glasses, and a protective suit. Meanwhile, for ethanol, inhalation may affect the nervous system, causing headache, possible dizziness, and unconsciousness. So, in case of inhalation, remove the victim to fresh air and keep at rest in a position comfortable for breathing. But in case of contact with ice, rinse immediately with plenty of flowing water for 10 to 15 minutes, holding the eyelids apart. Study on major equipment. Hazard study is compulsory because it provides a framework for assessing a whole production plant, one major plant item at a time. This allows for potential hazard arising from the operation that has deviated from design point to be found, and a plant profile can be created. So, for the hazard study on distillation column, what if there's no feed flow due to pump failure or mixture malfunction? Low liquid level in columns will occur. Thus, what can we do? We can introduce the low level alarm, but what if increase in temperature due to condenser failure, vapor present in the product, and flammable hazard may exist? So what we can do, we can install temperature sensor. What if less flow? So smaller feed rate and decreased liquid level in the column will occur. We can introduce also the low level alarm into the column. This hazard study also applicable for the isotropic column and recovery column. The hazard study on mixture. So what will happen if there's no feed flow due to valve failure? So low liquid level in the fermentation tank will occur. What we can introduce is the flow indicator. What if the increases in temperature occur due to condenser failure? There will vapor exist in the feed. What we can do, we can install the temperature sensor or vapor sensor. But what if less feed flow due to condenser failure or LIC failure? Smaller feed rate, decrease in liquid level in the column will occur. Low level alarm should be okay to be installed there. So, what if there's some contamination occur due to leak into fermentation tank? And then it will cause impurities in the solution. So we need to analyze the feed. So, move on to the hazard study on fermentation tank. So, what if there's no feed flow due to valve failure? So, low liquid or no product will be produced. So, what we can do, we can install flow indicator and low level alarm. But what if there's more feed flow? There will be flooding of fermentation tank due to valve failure and LC failure. High level alarm will alert us about it. What about less feed flow due to the condenser failure or LC failure? Low level alarm will alert us if there's smaller outlet stream rate or decrease in liquid level in the column. Lastly is the hazard study on heat exchanger. Well, if there's no flow from cold process stream or from hot process stream, so we cannot achieve the desired temperature and energy recovery cannot be achieved. So what we can do, we can install flow indicator and temperature indicator. What if there's more excess flow from cold process stream and from the hot stream? The consequences are the same with the no. So we can install flow indicator and change new valve or install temperature indicator. But if less flow from cold process stream and hot process stream, the consequences are the same with the no. What we can do, we can change a new control valve, install flow indicator and install temperature indicator. Therefore, performing hazard study are very crucial within chemical industry to obtain safer, more efficient and more reliable plants. Thank you.
Next is mechanical design. There are two major equipment that we have drawing according to the sizing. The first one is distillation column. This is the specific sizing that we got from the sizing and costing. And this one is the front view of the distillation column and the top view of the distillation column. The shell thickness that we got for the distillation column is 0.417 inches and the diameter for the distillation column is 37.81 inches, and all units for this equipment is in inches. This heat exchanger. For heat exchanger, we choose double pipes heat exchanger as our design. This is the overall of our design. We have shell side feed in as a hot streams and the tube side feed in as a cold stream. So this is the front view and the side view. So all you need is in inches.
Hi, then now we will talk about the profitability of the plant, checking it if it's viable to operate this plant. The first thing that we have to calculate is to find out the grassroots capital. From chapter 7, we have the equipment costing that would give us the total bare module cost. And from there, we can calculate the contingency fees as well, the CC and the CF. After that, we will be able to get the total module cost and then the grassroots capitals. These grassroots capitals will be used for the next part of the chapter. In order to calculate the total capital investment, the initial working capital is usually amount 12% of the fixed capital investment, whereas the startup cost is 8% of the fixed capital cost. So the TCI is actually equal to the FCI plus working capital and the startup cost. The calculation is based on percentage base of the grassroots capitals. So from here, in the end, we will get the total capital investment. It's about more than 200 million. Next, we will talk about the material, product, and the utility cost of the plant. The plant is assumed to operate 24 hours a day and 360 days a year. So for the raw material cost estimation, we found out that the cost per year is approximately 90 million. Then we have our product cost estimation, where same operation period is used for the calculation of this product cost. So we can see that the total sales that we have, annual sales, it's about more than 200 million as well. The rate of the utility costs are obtained from the local utilities company, rate given for the industrial use, and it's about 20 million per year. Then we will have to calculate the labor costs, where we need to have people operating our equipment in the plant. It is estimated about 15 people are needed per shift and total of 3 shifts per day, giving us a total of 45 people per day. So the labor cost in Malaysia is about 3,500 ringgit Malaysia per month, and that comes up to a total operating labor cost of about 1.8 million. Then we will move into our manufacturing cost and the total production cost. So the we will have to first find out what's the expenses. So we have the raw material, we have the utilities, we have the miscellaneous, that the direct costs, utility costs, miscellaneous costs, and indirect production costs will give us the total manufacturing expenses, AME. Then we have to calculate the total general expenses as well for administration, distribution expenses, and any research and development to improve the plant or the production rate. So um, the total production cost, APC, is equivalent to the AGE plus AME, excluding depreciation. We calculated depreciation based on 10% of our fixed cost investment, and our total expenses is 223 million. From here, we have the revenue from our sales, and then we will be able to calculate our net annual profit, ANP. Income tax is 35% net of our annual profit, which is about 4 million. And after deducting the annual income tax, we have our net annual profit after income tax, ANP, which is about 7.7 million. From there, we can calculate our after tax rate of return, RR, which is about 11.237%. Next, we will talk about the cash flow analysis. The profitability analysis of a cash flow series is to determine the payback period, the discounted payback period, and the net present value. So this is a summary of our cash flow analysis. We are assuming the plant to operate for 20 years, excluding 3 years for the plant construction, with a fixed capital investment of 223 million. And after calculation, the undiscounted payback period is 8 years, with an internal return rate of 8.42% if we want the payback period to be exactly 20 years, and the rate of return is about 11.24%. This is our undiscounted cash flow analysis, where we can find out what is our payback period. The first three value here is the total capital investment that are distributed throughout the 3 years for startup and everything. So from here we can see that this is the year that it will start to break even, and the payback period is at around the 11th year. So excluding the 3 years for plant construction, the payback period is actually 8 years. Then we have our discounted cash flow analysis, where we use different rate to find out different payback period. So we have 3%, 5%, and 8.42%, where by the year 20, we will estimate NPV equal to 0. For here, we have our cash flow profile for the undiscounted cash flow analysis, where the payback period is about 8 years, and also the cash flow profiles for various discount rates, where when the rate is 8.42% by year 20, in this case 23, it will start to approach the cumulative annual cash flow will start to approach 0, where the NPV is equivalent to 0. And the discount, this is the corresponding payback period after startup in year 3. So we have 8 years if the discount rate is 0, 10 years if it's 3, 13 years if the percentage is 5, and lastly 20 years if the percentage is 8.42%. And that's all from us. Thank you.